So it's a pleasure to open this event in Ludwig Qatar for electrophysics and on the members of each lab collaboration. We call the collaboration the mathematical stage, and lots of conversations and possible collaboration through the talk that will be a very varied character. So it will allow for the expansion of interest and perspectives and the possibility of different in the common in there. So I will to introduce Bruno Pizza and the thing that is called.
We have Paolo Piccione. He will be speaking about bifurcation phenomena in geometric variational problems.
Thank you to the organizers for having me speak about this theme. So my talk has to do with some geometry, maybe some spectra also, and maybe also have some genes at some point. So 3 words in the title of the conference will appear in my talk. Okay. Bifurcation is a very, very well-known mathematical problem which was studied since the 19th century. The iconic example is this problem of buckling of a metal bar under pressure. This problem has been modeled by Euler in the 18th century. So you have a metal bar and you put some load at the endpoints. So L is the length of the bar. The x-axis is vertical. So the lateral deflection of the bar is the graphical function W of x, depending on x. And this is the configuration for W equals 0 on the left. And on the right, you see a picture where W is positive. Okay. And so there is a constant, which is the elasticity constant, E. There is the force that you apply at the end, the load, the P. And there is a very simple second order constant coefficient equation that tells you what the shape of the bar will be. It's given by this this very easy equation here with constant coefficient. And we know how to solve it very easily. This is the sum of sines and cosines. And let's see. Yeah, the point is very weak here. And the frequency is determined by the square root of P over E, okay? So what happens is that, so this is the function, right? And now let's put boundary conditions. For P, ends means that the endpoints are fixed, okay? So W of 0 equals 0, this means that the initial point is fixed, which implies that B in this solution must be 0. And the other endpoint equals 0 says that A times the sine of lambda L has to be equal to 0, which doesn't imply, of course, that A is necessarily 0, because the sine can be 0. And the sine is 0 exactly when lambda takes this set of values. It's an integer multiple of pi over L, okay? So the result is that if P is less than this quantity here, I squared E over L squared, then lambda, the corresponding lambda is less than pi over L. So the only possible solution of the problem is W equals 0, okay? So there is no buckling as long as P is less than this value, this threshold value. However, if P is greater than this value, then you have more solutions given by all these values of 1. Okay. So when you cross this threshold value, there are new solutions appear. Okay. And the number of solutions can be arbitrarily large as long as the load is sufficiently large. So you have one solution, you give more energy to it, at some point it becomes unstable, and some new solutions appear. This is the basic principle of bifurcation. So these are the graph of the functions. This is the zero solution, and then when P is between these two values here, you get this other solution. The second solution, P increases, and you keep going like this. Do this solution exist in reality? Yeah, they do. There's one like that, right? Do other solutions exist? Look at this. Or look at this. They really all appear in nature. So the term bifurcation was coined by Poincaré at the end of the 19th century on a paper which was published by ACTA, journal, most famous journal, probably first mathematical journal of all times. And this is the title of the paper. And he describes the bifurcation as a topological change in the structure of a dynamical system, or a certain parameter that crosses a bifurcation event. So in the case that we've just seen of the buckling problem, the parameter P is the load, and the bifurcation values are given by this discrete set. This is the first appearance of the word bifurcation. Form of bifurcation. So it has to do with the loss of stability in something. Bifurcation phenomena appear everywhere in all applied sciences. Mechanics, if you study also electrical, very easy circuits like this, you have bifurcation of this parameter here, you can study. This you have fluid dynamics, Navier-Stokes equations, or phase separation of fluids, the Allen-Klein equation. Superconductors. It's really a very, very well-known phenomenon in many, many situations in physics and in economics. So let's put things in mathematical terms. So the way I look at bifurcation is a way to use instability. You have some trivial solution, some dynamical system. And then you, at some point, you add energy, you produce instability and create non-trivial solutions. Okay. So that's the way we formalize this problem. You have a set X, which is the set of possible configurations of the system. This is typically a large infinite dimension space, maybe Bach space or Hilbert space or something like that. And then you have a one parameter family of energy functionals. For each T, for each parameter T, you have a way of measuring the energy of some state. That's a real number. And so Ft of X is the energy of the state X at the time T, say, the value of the parameter T. And the solutions of the problems are critical points for this function Ft. Okay, so the Euler-Lagrange integration for the problem looks like this. The derivative with respect to X of the function Ft equals 0. And so suppose you have some, for each T, some kind of trivial solution for a problem. Typically, this is a ground state, which is like the minimum of the energy. So this means stable solution. So this is principle of least action says that minimize it what the energy are the solutions that you observe in nature. So you have, suppose that this is the graph of function x of xt of your solutions. And then you said that bifurcation occurs at some point xt star if there exists some sequence of instants tn that tends to p star as n goes to infinity. There exists also a sequence xn that tends to xt star as n goes to infinity, with the property that the derivative of ftn at the point xn is equal to 0, but xn does not belong to the curve. That is, it's not the point xtn, and that must exist for every n. Okay. So this means basically that the implicit function theorem for the equation dft of x equals 0 fails at the point xt star. This is what a bifurcation point is in mathematical terms. Okay. So if the implicit function theorem fails, that means that the assumptions of the implicit function theorem cannot be valid. So in particular, the second derivative of this function must be singular. Okay. So the second derivative, the first derivative is 0 because it's a critical point, but at that bifurcation point, the second derivative must be singular. However, this is not a sufficient condition for bifurcation; it is only necessary. And bifurcation theory is the theory that gives you sufficient condition for bifurcation. Okay. So for what I am concerned, a sufficient condition for bifurcation is given in terms of Morse index. So let me tell you what the Morse index is. So given a critical point x of your function ft, the Morse index of this critical point is, there's a formula here. I'm sorry, the pointer doesn't work, but it works well with the white here. So you take the second derivative of your function. This is the sum. So you take the self-adjoint operator given by the second derivative of your nth function, and you take the eigenvalues. Okay. And so these are real numbers, and you take the negative ones and you count them with complexity, and that's what's called the Morse index. In all these variation problems, the Morse index is always a finite number. Zero Morse index means stable fluid. Okay. So there's this famous theorem by Krasnodębski that says that you take the solutions at the endpoints of the interval xa and xb, and if there is some jump of the Morse index, you look at the Morse index along as t varies from a to b, and if there is a jump of this invariant, then there must be a bifurcation instant in the middle. Okay. So for instance, xa could be a stable solution with 0 Morse index, and xb an unstable solution with positive Morse index. And then you know that in the middle there must be some bifurcation. Okay. There's a lot of additional assumptions that I'm recording here. Of course, technical assumptions. You need to be second derivative to be a Fredholm operator. You need to have some non-degeneracy at the endpoints. But this is not a technical talk, okay? So we'll skip the technical assumptions here. So let me show you a toy example from calculus. If you take x, the state space would be just R2, and you take this function of two variables, ft depends on t, is this quartic polynomial in x and I, where there's this t factor in front of y squared, and you look at critical points of this as t values, okay? So the gradient, the differential of this function is given by these terms, and if you want this to be equal to 0, of course you need to have x equals 0 and y that satisfies a cubic equation. You see 2y cubed minus ty equals 0. So you always have the trivial branch solutions 0, 0. That's all. Okay. And you take the second derivative of this, the Sn, and it's given by this symmetric matrix here. And you count the negative eigenvalues of this matrix. And the eigenvalues of the diagonal matrix are very easy to compute because they're just the elements in the diagonal. So you always have one positive eigenvalue, which is 1. And you have another eigenvalue, which is given by 6y² minus t. Okay. And recall that y is equal to 0 along the trivial thing. So you have this is the path of self-adjoint operators along the trivial solution. And so you see, as t crosses 0, you have a change in the number of negative eigenvalues. So the Morse index is 0 if t is negative, and it's 1 if t is positive, right? So there is a jump Morse index at 0. So there is bifurcation at t equals 0. And in fact, the set of zeros for this thing produces this other branching rule given by this problem. Okay, so you have this. But this is called pitchfork bifurcation. So it has this, the shape of a pitchfork, of course. So for t less than 0, all the 0 is a minimum for this functional. But then when t is positive, 0 is no longer a minimum, it's a saddle point. Well, in this case, it's a local maximum, but and so the stability goes into this the bifurcating branch. So loss of stability, the stability goes to critical points on the trivial branch. Okay. By the way, I didn't make this up. This was Poincaré's example. Basically, he used exactly the same. This is from his Acta Mathematica. So, in case you wanted to blame me for using a trivial example, just keep in mind that Poincaré himself used it. Yeah. Okay. Now let's see if we can use this with more advanced problem. And I started looking at bifurcation problems when I studied this paper by these two guys that I'll show you in a second. And they were studying one of these equations that analysts log. You have Laplacian of some function plus some nonlinearity equals to it. Okay? And then you have some mixed boundary conditions. You have functions and normal derivative equal to on the boundary of some Paul. Okay. And these are in general hard equations to solve, but radial solutions are easy because for radial solutions you can write everything in terms of the parameter r, and everything becomes like a regular second order derivative. So you have like an equation, an ordinary differential equation like this, which depending on what kind of nonlinearity you're using, f, may be easy to solve. Okay. So if f is the like mind function, you have solutions for every positive parameter. Okay. And so there was this article published on Invención, it's very small and that said that you have some trivial solutions of the radial equation for every value of t. But as t goes to infinity, there's infinitely many instances where you have bifurcation from these radial solutions and you produce non-radial solutions. So let's say something like non-trivial solutions. So associated to bifurcation, you also have another important phenomenon which is called break symmetry break. Okay. So this is a kind of a picture. So radial solutions have this kind of shape. This is the graph of a typical radial solution in R2. And bifurcating solutions do no longer have this radial symmetry, but they preserve some kind of discrete symmetry. And I thought that this phenomenon was very interesting to study some geometrical problems where you have some kind of symmetry of a family of trivial solutions of some geometrical problem, and you want to create non-symmetric solutions.
Always like reducing the symmetry group to a super group.
That's what happens in general, yes. From a continuum group to a discrete group. That's what breaks the symmetry does. Yeah. So like you see the picture on the right have a smaller symmetry group, typically just a cyclic group, right? So I am a geometer, and geometers are interested in for instance, in submanifolds of like the Euclidean space. Okay, so an easy application has to do with constant mean curvature surfaces. Okay, let me tell you what the mean curvature is of a surface. So if you have a hypersurface in a Euclidean space, there's something which is called the principal curvatures. That is, you take normal sections of this surface. You have a curve, and you compute the curvature of that curve at that point. Okay, and so there are some special normal sections that give you special curvatures called the principal curvature. Like in dimension 2, there are the minimal and the maximum. So K1 and K2, or if you're in dimension n, you have n of them. And the surface has constant mean curvature if the sum of all these objects is constant and doesn't depend on the point when you do this. Okay, so the individually these curvatures may change, but their sum doesn't change. Okay, that's what's called a constant mean curvature surface. And these are very important surfaces. For instance, in R3, all the C and C embedded surfaces are round spheres. Okay, and this is strictly related to another very important problem in geometry, which is the isoperimetric problem. In R3, the isoperimetric regions, that is, the regions that minimize the area among all the surfaces that enclose a fixed volume. So in R3, the isoperimetric regions are spheres, and they're the only, in fact, CNC surfaces. But in other ambits, you have a richer variety of these surfaces. Also, in general relativity, constant mean curvature surfaces are important objects. For instance, the horizon of the events around the black hole is typically either minimal or constant mean curvatures at the surface. In which are the most famous constant mean curvature surfaces in R3? Okay, compact ones are only spheres, but non-compact ones, there's very many of them. And for instance, in the late 19th century, a French mathematician classified all the constant mean curvature surfaces that are invariant by rotation, and Delaunay. And he has this very nice construction. So you take your favorite conic, say an ellipse, and you take a focus, and then you let the conic roll on this line without slipping. Oh, okay. And you look at the curve traced by the focus of this thing. And now you take the curve, that's a roulette, and you consider the rotation of this curve around the axis, and you get a surface that has constant mean curvature. Okay, and all the constant mean curvature surfaces in R3 that are invariant by rotations are obtained in this way. Okay, this is a result from 1841 by Delaunay. If you ever go to Paris and go to see the Eiffel Tower, you will notice that there is, at some point, there is one of the stages of the tower contains the name of the most important French scientists. And there's few mathematicians, but one of them is Delaunay. And I have a personal, like, have you ever checked your ancestors, mathematical ancestors, on what's it called, the math geometry, right? And Delaunay is in my. So I have this personal thing, a person who knows it. I don't know if you. Sometimes I repeat things that my advisor used to tell me. Do you do this, or it's just I found he was a very smart person, and when I remember something. So I always, maybe he also repeated something that he's advisor. Maybe I'm saying to that things that I wish I was true, so I felt particularly, so I decided at some point that I should write a couple of his name on it, and I wrote some generalized Delaunay things. So I was particularly proud of this.
Just to be sure, is there a risky reason why you have to take some phonic to do this procedure? Like why not other shapes?
Yeah, basically it's related to the fact that it has to be a quadratic. So that means natural mechanics. Basically. Yeah. It's a second order thing. Really.
So it's okay to repeat until someone actually writes it down and then it becomes a dogma.
Yeah. But also I was very happy when I saw this. So the Delaunay surfaces include undulatoid if you take an ellipse. But if you take a parabola, I take the focus, then the roulette is a catenoid, okay, which is the minimal surface. If you take a hyperbola, you get a nodoid, and that's not embedded. And if you take, I'll leave as an exercise to see what is the figure in case you have a circle rolling. Can you imagine what the corresponding surface is? Yeah, that's it. So you have, depending on the eccentricity, you have these different pictures, depending on the. Oops. Yeah. Oops, I should have. Sorry, it never works. Sorry. Delaunay would not have liked this. Sorry. So I started studying bifurcation for CMC surfaces. Okay, I've seen this famous paper by Marcel Paccard that studied bifurcation from nodoids. In a sense, all these surfaces, these Delaunay surfaces, can be obtained as bifurcating from a cylinder, in a sense. So a cylinder is, like a trivial CMC surface, but then you pass to other, like you create eccentricity in the conic and you get other solutions. Okay, so you have to think of these Delaunay surfaces as bifurcating branches from cylinders, in a sense. So these are physical examples of these bifurcating nodoids, let's say. These are in this German Museum of Mathematics. Notice that these solutions are no longer rotationally symmetric, but they preserve some discrete symmetry. This is what happens here. So one of the results that I did with a couple of colleagues, Miyuki Koizo, Ben Palmer, was to study fixed boundary problem related to this, and we also proved the existence of bifurcating nodoids with fixed boundary using bifurcation theory. And also, I decided that in order to commemorate this ancestor of mine, I should do something about generalizing the Delaunay surfaces. And so I studied this problem of bifurcating Delaunay surfaces into CMC surfaces, and we call them new Delaunay surfaces. The setup is this and that, and now I have to be a little more technical, but I hope you don't mind at some point that I say something more advanced. So what we consider a manifold, like instead of Euclidean space, some other curved manifold with some metric, which has some symmetry. So it has homogeneity. One means that there is a group action that preserves the metric, and whose orbits have codimension 1. So think of, for instance, well, let me give some examples. So what this means is that the quotient space is dimension 1, so codimension 1 of the principal orbits. So the quotient has to be a manifold with singularity. So it basically has to be a compact interval. So with two critical points. And these include a lot of examples, including these exotic Kerber spheres, these spheres with non-standard differential structures, or spheres of complex or hyperbolic projective spaces. So, so the orbits of this group are necessarily have constant mean curvature because they're homogeneous, and so everything is invariant by the group actually, including the mean curvature. So it has to be constant. Okay, and so these principal orbits have all the same topology, but then there are two special orbits at the end, sigma 0 and sigma 1, which are singular in the sense that they lose dimension. For instance, cylinders, they are orbits of a group which is given by rotations and translations, right? So you get the orbits of cylinders. But as the radius of the cylinder shrinks to 0, then you have a singular orbit, which is the axis of the cylinder. So this is a similar situation. We have this sigma t, these are hypersurfaces, but then they collapse, they lose dimension at these two endpoints, okay? So we have this collapse phenomenon, and we have CMC surfaces invariant by this big group, and then they collapse. And what we prove is that as they collapse, bifurcation must occur. So when they collapse, their mean curvature goes to infinity in a sense, even if it's constant, of course, because the curvature of a very small circle is very big, right? And as this happens, like for the Buckland problem, you give more energy, you give more curvature, it goes to infinity, you must have bifurcation there. And you create new solutions which are no longer invariant by the entire group. So they lose symmetry, but we have infinitely many of them. And this is what we call the new Delany surfaces in this situation. So these are dedicated to this former. For instance, a very easy example is the three-dimensional sphere in our floor. So you take, in C2, you take the pair of complex numbers whose sum of squared modulus is equal to 1, that's a sphere. And inside them, there are some tori. This is the projection in R3, the stereographic projection of this tori inside S3. So you fix the value of Z and W, okay, and that gives you torus for the two circles. And they have mean curvature, they have constant mean curvature because they're invariant by a torus action. So these are principal orbits, but they collapse to circles at the endpoints. So as t goes to 0 or to 1, you see that one of the two objects becomes 0. And so rather than a torus at the endpoints, you have circle. So you lose dimension. And the mean curvature is given by this function, tangent plus minus cotangent, wherever. And you have these two singular orbits. As t goes to 0, we have Delaunay tori also in spheres, okay? And we know that they cannot be invariant by rotation because the only tori invariant by rotations belong to this family of. By the way, these are called Clifford. So this is an example of such objects. This preserves a Z3 symmetry, this is a Z4 symmetry, Z5, and so on. So basically, we have for every n, we have a Zn invariant torus, a constant mean curvature torus inside S3. And the proof of these results are all the same. The space of states with all possible embeddings of your torus into your ambient manifold. And the function you want to minimize is area plus h times the volume. This is a Lagrange multiplier problem, right? You want to maximize the area with fixed volume, right? So you have function area and volume is the constraint, and the Lagrange multiplier is h, the constant, the mean curvature. And so a critical point is something which has constant mean curvature. And so we look at the Morse index of sigma, and that's easy to compute. It's given by computing the eigenvalues of the Laplacian operators plus a potential which is usually a constant function. And then we observe that the Morse index goes to infinity when the surface collapses. So we have infinity main bifurcation by presence of script here. Okay. Another application of bifurcation theory has to do with the Yamabe problem. Let me introduce you to the Yamabe problem. So another result by Concord is this uniformization theorem that says that if you have a closed surface that is a two-dimensional manifold without boundary, so and this is where the genus enters. So genus 0, for instance, is a sphere, genus 1 is a torus, right? Higher genus. Then what happens is that you can always find metric of constant curvature on each of these surfaces. In fact, given any metric on this surface in the conformal class, you can modify this metric by a conformal factor, and you obtain one which has constant curvature. Okay, and for genus 0, the value of the constant curvature is positive. For genus 1, the value of the constant curvature is 0 always. And for a higher genus, you have negative curvature. Okay. So, but this is a very two-dimensional result. Okay. So you want to ask yourself what happens in higher dimension. Okay, this is what I was saying about conformal dimension. This is an example of what is a conformal deformation. Conformal deformation of a metric is a new metric which has different lengths but preserves the angles. So this is the kind of changes that you can have when you apply a conformal change to your metric. Okay. So mathematically, this means that your metric is multiplied by some positive function u, and for some reason we want to raise u to this somehow, or this will make some equation easier. So the conformal class of a metric is just a set of all metrics that are obtained multiplying your g with some positive function u raised to some power p. So this is the topology of positive functions of m simply. This is just a set of positive functions. Okay. So this famous Japanese mathematician who died very early, Yamabe, he formulated a generalized result about constant curvature with the following setup. So you take an n-dimensional Riemann manifold, and you consider conformal changes of this metric by multiplying g with this function u raised to this weird power for some technical reason, okay? And you want to study which ones of this conformal factor will give you constant scalar curvature. Okay? And having chosen this special power for you gives you an elliptic equation, a quasi-linear elliptic equation in U, given by this. So Laplacian U plus another linear term, which is U times the scalar curvature, equals to this nonlinear term here, C U to some power n plus 2 or n minus 2. So the reason why we've chosen this power for U is to have the easiest possible equation, which is this equation. And this turns out to be a very hard equation to solve because of the special nonlinearity that appears here, n plus 2 divided by n minus 2, which is exactly the critical Sobolev nonlinearity. Okay. For this type of equations, it is not known the existence of a positive solution. Okay. And Yamabe in 1960 wrote a note in which he claimed that he proved the existence of a positive solution, but he never published it. He put it in the book. Okay. And then he died very young and very tragic circumstances. And two students of his went to his office, opened the door, found this note, and published this with his name. So there was this paper published after his death with his name, claiming the existence of a positive solutions for this equation for every compact manifold time. But the proof was wrong. And Yamabe was blamed for this, but it was not his fault, it was his students' fault. So if you have students who take too many initiatives, you should make sure that your private notes, so that was his paper, but in 1968, Schrödinger found a mistake. Okay. And this was a very subtle point, very subtle, which had to do with some estimates on this, a priori estimates on this equation. So he showed what the problem is, and he proved the existence of a positive solution for this under some restrictive assumptions. And then Aubin extended the proof, and finally Richard in 1984 proved the last case. So in fact, the result Yamabe's result is true. It is true that for every compact manifold, you have a positive solution for this equation. And that gives you, in every conformal class of a compact Riemannian manifold, at least one metric of constant scalar curvature. Okay, but this was a combined efforts of all these people. So this is the final result. There's a compact missing here. Every compact Riemannian manifold permits a conformal deformation with constant scalar curvature. This is a very deep theorem. It uses even the positive mass theorem in general relativity. So it's really good. So now the question, of course, is uniqueness, right? And so I've studied non-uniqueness using bifurcation again. It's sort of another 5 minutes. I know people are getting tired. So if you take a homogeneous manifold, so it means that there is a group of symmetries that acts transitively. Then, of course, the metric has some delta. Okay. And so, in a sense, for homogeneous metrics, you have trivial solutions that are coming from the homogeneous metric. Okay. For instance, if you take a product of a sphere times a circle, and you change the radius of the circle, t, and then you let t goes to 0. That is, this circle shrinks to a point. So the idea is that when you have some trivial solutions that shrinks to something, the energy explodes. There must be bifurcation. Basically, that's the idea. And so they prove that this is the case for this sphere. And with some colleagues a few years ago, we proved a similar results if you take what's called a cross, that is a compact rank 1 symmetric space. Spheres, projected spaces, scalar planes, something like this happens. You multiply by some closed manifold with positive scalar curvature. You take the product of them. So rather than Sn times S1, we take any cross by any closed manifold with positive scalar curvature. We multiply them and we take the metric on the second factor shrink with this factor t, and then as this factor shrinks, we have infinitely many bifurcation points. So infinitely many solutions for the Yamabe problem also in this case. And also, rather than taking products, we can take more general objects like fiber bundles. So these are all fiber bundles on the manifold CPN. So the 2n plus 1 dimension projects onto CPN with S1 fibers. Okay. So this is not a product, it's a more general object, which has some topological interest. And so you have, you have the same thing for quaternions projective spaces for this other Hopf vibration. And you have Berger matrix, which is you take the horizontal matrix on CPN on the spheres. This is just the round sphere, and you take another metric on the fiber, which is G vertical, and then you shrink the fibers again, and as t goes to 0, so you rescale this as t goes to 0, you have infinitely many solutions as t goes to 0 again, using Berger. This is getting probably a little tired for you. Let me see. Yeah, I have 50 minutes. Let me see if I have something more interesting to say. Maybe just mention that the very last thing. We also managed to extend this to a singular problem with bifurcation. So suppose you take a closed manifold, for instance, a sphere. You take a closed subset and you remove it from it. So, for instance, you take a lower dimension sphere. You remove a lower dimension sphere from a large dimension sphere, and you want to find now a complete metric on the complement of this set, which has constant scalar curvature. So you want to solve the Yamabe equation by prescribing with solutions which have prescribed singularity. Okay, if you want to find a complete metric on the complement of some set, then the conformal factor must explode at the singular points to make it metric complete. Okay, and using bifurcation, we find infinitely many solutions to this problem when you take. So you take. There are infinitely many complete metrics on Sn time minus Sk, which are conformal to the round metric, and which have constant scalar curvature, which is a quite surprising result because you would not expect something complete in the conformal class of a round metric and that still has constant curvature. So I think this is the last result there.